So welcome to the last part of lecture 33. In this part, we just kind of want to look at some consequences for symmetric matrices. Okay, and from above, we know that if you have a symmetric matrix, there's a basis where you can diagonalize the matrix. Okay, so but actually you can get something else out of this. So you can write it as u1, u2, u3 up to un times the matrix lambda 1, lambda 2, up to lambda n, 0, and then times the inverse of the matrix whose columns are u1 to un inverse. Okay, now let me just add some comments here. So u1 through un is the orthonormal basis of eigenvectors of V, and that would be, in this case, say Rn, and the lambda i's are, of course, going to be the eigenvalues. Okay, so when you have a symmetric matrix, what you should think about is that the columns, when you diagonalize it, you get a matrix corresponding to the eigenvalues. The matrix out in front, the columns inside of it actually form the orthonormal basis for the vector space Rn, and this matrix over here is the inverse of this first matrix. Okay, but now we can actually say a little bit something else about this matrix on this side. So you know from Math 1B03, it's actually very hard to write down the matrix, the inverse of a matrix automatically. If I gave you a matrix and said, okay, quickly tell me what the inverse is, it's going to be quite difficult because you got to crank out a lot of things. But it turns out, and if you took Math 2LA3, you may have actually proved this, that if you have an n by n matrix whose columns are orthonormal, right? So each column has norm 1, and their inner product with each other is, each of the columns are orthogonal, then the inverse of the matrix is simply the transpose of the matrix. Okay, and let me just quickly give you a proof of that. Okay, well, because inverses of matrices are unique, it's enough to show that if we take the transpose of U times U, it equals the identity matrix. So right here, what I've done is I've started to write out the entries of the transpose of U, and let me just write down what U is, right? So this is what U looks like. Right, so I'm writing down all the entries. Okay, so UNN. So just remember that, right, this is U1 is the column corresponding to this, U1 corresponds to the first column, U2 is the second column, and UN is the last column. And notice when we start to fill in this matrix, I'm not going to write it all out, but we would be taking this row, pairing it up with this column. And that would be the same thing as taking U1 dotted with U1. But now if I take this row with this column, okay, this is the same thing as taking U1 dotted with U2. Okay, right, because the first column here, or first row is U1, and then the second column is U2. So you're actually getting over here is U1 dotted with UN, because these guys are the dot product, right? So this is the dot product. So then you're filling in this whole matrix. So then here you get UN dotted with U1, dot, 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 and then UN dotted with UN. Okay, so you have a whole bunch of dot products going on here, and you have to remember that these are all orthonormal columns, right? So ui dotted with uj is 1 if j is equal to I, and it's 0 otherwise. So when we go back to our matrix, we get all ones down the diagonal, but if you're off of the ones, you get 0, right? So that means that this matrix right here is equal to the identity matrix, which is what we wanted. Okay, so this is great because we're looking at a symmetric matrix. We can break it up into this form, and we didn't know necessarily what this is, but the fact now tells me how I can quickly write down this matrix here on the right. So if A is symmetric, we can write it as in the following way. So you have your U1 as your first column, and the first row is the transpose of the first column, and then the second row is the transpose of the second column, and so on. So there we go, there is my matrix. And then we expand it out. So if you're taking the first row and you're multiplying it by lambda 1, what it does is it scales the first column by lambda 1. The lambda 2 here scales the second column by lambda 2. And I still have U1 transpose, U2 transpose, up to UN transpose. And when I expand this part out, what I get is lambda 1 times U1 times U1 transpose. So this isn't the dot product, right? So this is a column and this is a row. And then we get lambda 2 U2 times the vector U2 transpose up to UN times the vector UN times the vector UN transpose. And each of these guys right here, this guy, and so on, these are n by n matrices. Right? So these are n by n matrices. And to see why that is, this is an n by 1 vector, and this is a 1 by n vector. So we get an n by n matrix right here. And what this guy here is, this big thing here, is called the spectral decomposition of A. So this is called the spectral decomposition of A. And maybe it hasn't been too clear, maybe you've seen this word spectral, right? So spectral, refers to eigenvalues. When we talk about the spectrum of an operator, we're talking about the set of all of its eigenvalues. So it's called the spectral decomposition, right? Because you can see your original matrix, you're breaking your matrix up, and you can see the eigenvalues in there. And not only that, you also see the orthogonal basis of the associated vector space coming from your operator. So there's like kind of a lot of information embedded inside of this decomposition. Okay? And just as a final comment, okay, just hopefully to help here, is that when A is not a symmetric matrix, you can't find a basis of eigenvectors that's orthonormal. You may be able to find a basis of eigenvectors, but you can't make those eigenvectors, that basis, orthonormal. Okay, so there's a lot of kind of deep results here. I know we're getting further into the course, and like it may seem a little overwhelming. Right now, I'm just kind of making sure that you kind of understand the big ideas. So we want to know about what the complex spectral theorem is, the real spectral theorem is, and the spectral decomposition. Okay, so we'll stop there, and we'll move on to section 7.3 in the next lecture. Okay, have a great day.